be comfortable. I will try to be not so fast, but also not with much details. We have many slides. I have tried to make slides self-contained. So then you can, all slides have links for the original physics analysis summaries or papers. Then after, if you want the talk, I don't know if it is possible to make it available for the audience because it's too big, yeah, because of the figures and plots. Then, but you can, I tried to make them more with a lot of information for you to work with the different analyses, different results. We have we got in this last year with the data of 2016. Okay, so here you see I am, so for the ones who don't know me, I am postdoc in the Brazilian Center for Physics Research. I am postdoc there since 5 years, okay, always working in CMS collaboration. And but I did my PhD in phenomenology, in theory, so I know the needs of the phenomenologists and theorists, in minimum, yeah, okay, at least. And I also work in the Filter Circular Collider collaboration. CBPF is the Brazilian representative with us, okay, in this experiment. Well, okay. Well, this is a CMS. Here you see the size. It's not working. No. How it is? Here you see the size of our experiment. Michael Hoare, our artist, physicist, and artist, is inside the detector to have an idea about of the size of the experiment. So we are 25 years making science, art, and also our outreach. Okay, so the letter of intent was released, submitted in the 1st October, and concerning the outreach, we have already almost 23,000 people from 40 countries. We do virtual visits. People go, schools, people, groups from all Europe and also United States, all continents come to CERN, to CMS P5 in CC in France to visit the experiment. They go down, they 90 meters, 100 meters down to visit the detector when it is opened. And also we have received some prizes, some awards concerning the art at CMS. So Michael Hoare is the one, he's a photographer, and he has published a book with CMS members, with many photos from CMS. Very nice book. So we are for 25 years and ready for the next 25. I hope hope to be here yet. So this doesn't work. Okay, so in this slide, I give you an overview of the performance of the LHC. So we have reached, oh sorry, there is a 47, 40, so in this first plot, 47.1 in 2017. We intend to reach 150 femtobar inverse at 13 TeV by the end of 2018. And also important to say that LHC has reached the Lumi target for 2017, 19 days before our end of year. Okay, we have a change in the schedule. We didn't have any. We didn't the heavy ions runs in the end of the year didn't happen it, and we are going to start the 5T VPP reference run and low energy high beta run now on Saturday in this week. So we are here, okay? So in this week we had this 5T VPP reference run, and after that 2 weeks with this run, then the machine development number 4, and after that the technical stop. We come back in March 2018, okay? Interesting to notice that we had a few weeks ago the Shannon run with heavy ions. I put a slide in the backup if you want to take a look in some information about it. And also we had oh my God, no, this is no. Sorry? It was planned to have this collision because of some studies for other experiments. So then, as they not experiments of the LHC, but outside the NA something. Oh, sorry. They took the opportunity. Then the CMS Atlas and the other experiments took the data. Sorry, I didn't understand your question. No, it's in between. It's in between. Yes, it's in between proton and lead. Yes, I moved I will show you the okay in the backup. I will show you because of 50 slides. Okay, so I will show you. It's in the between lead and proton. Okay, well. We have this peak in the instantaneous Lumi, okay, and so the average pileup has increased a lot. Then we had to LHC try to maintain the pileup average at 35 during. So it has happened in the 9th October, okay. So this is a good, how can I say, a good example what we expect for the next, for the run 3. Yes, when we have the high Lumi LHC scenario. Okay, well. Okay, so. The detector update for the next phase, so the phase 1 for the 14 TV, we had so we had changes in the H-cal, in the gas electron multiplier, and also in the forward hadronic calorimeter. But the main differences were applied in the pixel detector. We have many, so this news in the pixels, so the number of layers increased. You see here it's from, so here is the interaction point, so 50 centimeters away from the interaction point. We have different, so this is for, this is the current one, okay? This is the upgraded one, okay? And so in the barrel, and in the forward, not forward, but up to pseudo rapidity 2.5. So here you have we have new pixel forward layers, So we have tended from 3 to 4 in the bar and to 2 to 3 in the end caps. Okay, we had so many differences, and also the cooling system was updated, so a reduction in the material, and so it was very challenging. Nowadays we have some problems in this DC-DC conversion that delayed our data taking, but it is already being solved. The guys are taking care of it. Okay, so to see how this phase 0 and phase 1 detector changes the efficiency of the heat in the heat of in pixel. Yes, so you see that in this LUMI, so in the 1.4 instantaneous LUMI, we see a decrease in the efficiency, strong decrease in efficiency. And when we update the detector, so the estimation is to maintain more or less reaching so maximum 98% of, so not losing a lot data because of the detector. Okay, so you see here the difference in the efficiency of the detector between phase 0 and phase 1. Okay, so this is the plot I wanted to show you yesterday, but okay, this is the future. So the high, not so this is the close future. Yes, so the high luminosity LHC. We are here. Okay. And, well, in the end of 2018, we start the long shutdown, the second long shutdown, where we do the upgrades showed in the previous slide. And then we start in 2021 with the phase 1, increasing the, so maintaining, so we are going to increase the energy now in this in 2018, and then maintaining in the run 3 for in 14 TV until the end of 2023, when we start the third long shutdown to start the high lumi LHC. Okay. Here you have an idea about the average by lab and the LUMI, the instantaneous LUMI, the expected instantaneous LUMIs, okay? Luminosities, yeah. So in the long shot, so we are here. So sorry, this line is shifted, so it should be here, okay? But so we are here. So we have an average by lap of 35. We work in Monte Carlo and data with 35 average by lap. And so for the second long shutdown, we wait 50 at least, okay, or even more. Yeah. So for the run 3, for the 14 run here, so it corresponds. This is the high lumi. Yes. Then we will increase a lot the pileup, and so many changes have been it is needed to happen. So here next week, yes, we had the workshop of high lumi and high energy LHC. This is the Indico. You can take a look. Very interesting result prospects for physics and the detector. Many talks, very interesting, and it's very useful with useful information. Okay, so for the phase 2, this is the high lumi LHC program. Okay, we need many changes because of all the consuming, yeah, of the detector, so new LUMI monitoring beam, so end cap calorimeters, triggers, trackers. So we will renew all detector to be prepared for the very high pile-up in this scenario. But from 2025, we are going to see results. So after the long shutdown 3, okay? So if you want to take a look, now here again, the Indico page to see results and the changes in detector, all performance plots, and it's very interesting. It was a very interesting workshop. Well, let's go to the publications. So we have more. So here, 600. I don't know why it's always showing this hand here, but forget. Okay. Okay. We have a lot of data papers published. Okay, more than 650. So 671 collider papers published. But we have reached 700 papers submitted. So, unfortunately, there is no space, of course, to cover all analysis here. I have chosen with the approval of the CMS collaboration, the public ones, of course. And if you want to take a look in all public results, for sure you know this page, okay? But so I put here the link, and unfortunately, I could not include the interesting results from heavy ions, from forward physics, among others, in this talk. So if you want any specific result, you can ask me. I can try to find it to you. Okay? So, in general, the standard model is going very well. Okay, so far no surprise. Yes, and you see our measures. So we have here the legend. So 7, 8, 30 TV measurements with our final luminosity here. Okay, so the theory prediction and also the limits, the exclusion limits. Okay, so you see that the theory prediction is very so in agreement with all the measurements. Here the 3W production we did in 8 TV. I participate from this, so we had an exclusion limit, upper limit in the cross section here, because at 8 TV we didn't have enough LUMI to measure this production, but we intend to do it 13 TV. But the others, you see that are all in very good agreement. Okay, this plot can be reached and with more details. Also, other plots in this link here, if you are interested. Okay. So let's. So I have shared not. I have shared analysis not according groups, because we have groups, as you know, for each kind of physics. Okay, but I didn't share as groups, but as subjects. Okay, so concerning Higgs, we have many analyses. First one. So here is the link, as I promised you, for the papers and or physics analysis summaries. So the update, we have Higgs has its properties updated. Okay, so this is the most important channel now for the Higgs plot, because we can reconstruct the final state decay product. So it's a very nice plot here. We see the very nice signal here. Okay, we had this. So the full LUMI of CMS, certificated LUMI. Yes, because we certificate when we get Data, we have recorded data, but after that, after recording, we have a group that certificate all data to be available for the analysis, okay? I work in the, not in the certification, but in the particle physics data sets with the validation of CMS software. Then, so we work with all these guys, making the data and also Monte Carlo available for the analysis. Okay, in this channel, we have also concerning the new physics, so the anomalous triple coupling, so Higgs to Higgs to gauge bosons, exclusion limit, including operator, CPU violation operator. You can get this result in this link. So you see that the systematics are very high, yes, so reducible background. So you see the numbers here are very high, and so this is a channel, although it's very nice to see all the results, but the estimation of the systematics are still high, and we intend, so you are going to see in the next slide. Here you know, so the background, the signal, what we have observed, and the expected one for each channel, okay, for leptons and 4 electrons for muon, 2 electrons, 2 muons, and also in the combined channels. You have here the results in the case you want to compare with your analysis. And here I show you what so the signal events we could see. Okay, so this for sure it extrapolates the background. Okay, so it's a very nice measurement. And for the cross section, yes, so you see here the no, what is this? No, this is the signal strength. Sorry, forget the signal strength modifier. Okay, so you see very close to the standard model, and here the property, so the signal strength, and then here the new measurement of the Higgs mass based on the likelihood scans, and also the width. So you see here for this range of 4 lepton mass. So all new limits updates in the Higgs properties. Also, we have measured the fiducial and differential cross-section based on our fiducial phase space is defined like that. So here you see the lepton kinematics, and below the event topology, how we deal with the events to measure the cross-section. So the fiducial cross-section like that. You see against center of mass energy. So we had an improvement here, and so the standard model gave us 2.76. Now the fiducial 2092. This is the last updates, and here for the differential cross section, this is interesting when we do the distributions in phenomenology. Yeah, so you see here. In the Higgs, in the PT of Higgs, we don't see any event larger than with PT larger than 200 GeV, at least with 13 TeV in the 13 TeV scenario. Okay. Well, for the High-Lumi LHC, so very close future, we see, so you remember the the systematics before. Yeah, so maybe we have an improvement in this measurement. The prospects make the PAS, the physics analysis summary, for the High-Lumi LHC. The link is here. The number is here. This one. So you see here for the 13 TV. So the plot from the previous slide, and the prospect, it would be very challenging for the theoretical precision, this new data. Okay, and also it would increase the sensitivity for new physics, for sure, with high luminosity, with the high luminosity run. Okay. Well, here changing to Higgs to photon, we have we have the measurements in also for the fiducial and differential cross section based on this phase space. We have measurement the ratio of PT against invariant mass, and also in the eta region. So you see the fiducial new results of the fiducial cross section here. So 84. The theory expects 75. So we have this difference, and here you see a very nice. So the background, the diphotomass spectrum, okay, weighted by this ratio, and you see the peak here in the invariant mass of the photon. You see the peak here in the 125. Nice plot. This one. Also the number of jets. Jets, right? No. No, leptons. No, photons. Yes. And the PT of the Higgs, of the system to photons. Yes. So you can compare with your results in phenomenology, and more of resonances. So the new, searching for new resonances in this same channel. We have we have tested the mass range between 70 and 120, 110. Okay, so we see here slight increase in significance for this mass, for this invariant mass value. We have here the plot, also the local p-value here. Okay, so this would be followed in the next year to confirm or not. Okay, this local significance. Well, if you want more details, so you can get so easily in the paper, but let's see what it happens in the next year, right? Well, we had an observation of the Higgs into tau through we analyzed the gluon fusion, vector boson fusion, and the boosted channels. Okay, we had this very nice significance combining all results 7, 8, and 13 TV. Was the first experiment observation of the Higgs boson Yukawa coupling to tau leptons. You see here the signal for so the combined, okay, and the predicted Monte Carlo distributions. So you see very nice signal here, okay, and it was a very good analysis. So very interesting. The first time seen in the tau leptons. Also, is still in the observation of tau leptons. We have, I show you here the signal strength per category of each scenario, of each category of the analysis, okay? Well, the combined is so 1.9, the signal strength, and also here the couplings, yeah, the couplings of the Higgs to the vector and to the fermion. Okay, so you see the exclusion limit here to compare with the phenomenological studies. And next, okay, so nothing more to say about tau. We change to the evidence of BB bar, Higgs in BB bar. Also, so it's the production mode with gauge bosons, okay, exploiting categories with no 1 and 2 leptons, and we had this combined and control regions to extract the signal. Well, using also BDT, yeah, machine learning techniques to differentiate signal and backgrounds. Here you see the significance, so the log of the ratio signal to background, and the invariant mass of 2 jets, 2 leptons, sorry. And you see here the signal, okay, in red, the nice peak here. And now, so the evidence, because we had the combining run 2 and run 1 and run 2, we have 3.8 significance expected and observed. So it's not 5, and we only can guarantee the evidence. Next year, I am sure we have more developments about it. Well, also in the BB bar final state is another analysis. Yes, so it was used the boost Higgs to BB bar. Okay, so we have a high PT greater than 450 to identify. So it was identified using the jet substructures and the dedicated B-tagging technique. So in the jet substructure, I put this information yesterday because I noticed your interest in the jet substructure. So it was used the soft drop grooming, okay, and I put here also the paper, the theoretical paper about it, to remove. So this technique removed soft, and it's good to deal with pileup and the line event from jets. Okay, so many analyses with boosted final states are using this soft drop grooming. Okay, we are going to see others in the next slides as well. So this is the mass of the jet, of the 2 jet, so the combined. So it's based on this, so mass, soft drop mass. Okay, and we see here so for sure it's the first observation of Z, because so this is the background, yeah, and the second topology. We didn't reach good significance in the Higgs, but we could measure the Z, and this measurement was used as orientation, yes, as a template to confirm the method to measure the Higgs. And but we had proposed this limit cross section. Production cross-section in this phase space. Okay, so 74 femtobar but you see that the statistics is very high, okay? So we need more data to take care of it, okay? Now we have the Higgs so in this final state, 2000 BB bar. This is we are taking a look in resonant in the mass range, the higher mass range, and non-resonant production as well for of the Higgs boson pair. We can study the Higgs self-coupling, as you said before, of the three. The three Higgs coupling. Okay, so based in this modified standard model Lagrangian, I informed the couplings, the definition of the couplings, and here these models. So we probed the radions and gravitons as in this model, and as well and the two Higgs doublet model to induce resonant double Higgs. Okay, so we probe these models in this analysis and so the results. Well, you see here the selection criteria, okay, based on the transverse energy, the eta, the invariant mass, and PT. The categories were shared between high purity and medium purity category for the MVA training, so the multiple variable analysis in to differentiate signal and background, okay? And what we've got after assuming some details of each model for the spin zero, so for the region here, we have excluded all mass points below 55, so you see more or less, yes, here, okay? So below, okay, here this is 1. No, I guess I changed the, no, it's right. Okay, no, it's right. Yes, I changed no, it's okay. For so for gravitons, we have here, okay. No. So the mass point below 550. So you see here, okay. So all excluded in this region for lambda R3 TV, okay. So below the bulk radion here, and in the case of the graviton, sorry. And in the case of radion, we have excluded from 280, okay, until 900. So it's for more or less here, yes, 800 in fact, okay. So all this part, assuming this red curve here, okay. So we have, so the limits, the exclusion limits on the mass of these particles, expected particles, and is still on Higgs BB bar, gamma BB bar. For the so that the slide before was for the resonant production. Here, for the non-resonant production, we reached the cross section of 1.67 femtobar. You see here in this plot the combined all combined categories, okay, based on the beyond the standard models we assumed, and the Higgs self-coupling, the K kappa gamma is excluded in the limit in this limit, okay, -8 to 15. And here you see the two-dimensional plot of, so this is the standard model one, the point, okay, and the two-dimensional plot related to the kappa top and the kappa lambda couplings to have an idea about the exclusion. You see, okay, you have different curves here, and you can take a look how it matches. So the standard model is the red point. Okay. Another Higgs result is the evidence of TT bar and TT bar Higgs, and so we took same sign to leptons, 3 leptons, 4 lepton channels. Although the 4 lepton was not so the limited statistical power, and we see that we've got the significance. So after this signal strength, so the BDT we used the boost decision tree as well to classify the outputs, and so a combination of distributions. And with this combination, we've got so the signal strength 1.5, okay, in the multi-lepton channel, and this observed yield was corresponds to a significance of 3.3, okay. So they observed it, and this is evidence. So with more statistics in the next run, maybe we can improve and finally observe this channel as well. So next 2018, it's very, maybe it will come with many not surprises, but many confirmations about channels. Also, the flavor violating the Higgs decay, we put some constraints on the Yukawa couplings of diagonal Yukawa couplings. We had an excitement in run 2 with an excess of 2.4, okay, but now it's more constrained. So the limits you see here in the branching ratio, okay, with this BDT fit. And here also the upper limits of the diagonal Yukawa couplings for your own models if you need, okay. Here, yes, okay. So you see here the difference, okay. So for the Atlas, for the CMS 8 TV, for the Atlas and CMS 13 TV, we have constrained even more the limit, okay. It's okay so far? Good. I will change the topic, okay. Now vector boson scattering. So vector boson scattering, it's very nice to me because I like, it's my preferred subject for my PhD, and I try to work, although many so if you don't know, you know, of course, vector boson scattering, the topology. Yes, we have a proton, and then to the decay in the center, in the center of the detector, and 2 jets back forward. Yeah. So this is a very important channel to probe the electroweak sector of the standard model. So far, we have been trying the leptonical final states for obvious reasons. The pileup of the jets in the LHC is very high, and so we had good results with the same sign lepton, final state. The opposite sign is hard because of the top background. And so in the semi-leptonic final state, we have started 2 years, 3 years ago, the analysis with the semi-leptonic final state. So this is my beloved one because of my PhD, yeah. And but it's very hard to work with because of the larger backgrounds. But now, we are working in 13 TV, and we are going to work in 14 TV. So we are focusing on the boosted jets to try to get some results. I will show you the same. So the one I will show you is the same sign leptonic in the VBF topology of the same sign W, okay, same sign leptonic final state. We have observed 5.5 sigma with so the signal is trained very nice, and also we have limits in the different new physics models. And also the fiducial cross-section for this channel, okay? So you see here the fiducial cross-section. And for the new physics, we started, so with the doubly charged Higgs, we excluded the masses below 460, okay? We excluded in this model independent limits, and this George, this George Mashak, I don't know exactly which model is this one, okay? So if you know, we have excluded the double, so this double charged Higgs with mass below, also around 460, so the same exclusion limit in both models, okay? So this is for the specific model, and this is a model independent, okay? Also limits on the anomalous quarter gauge couplings with dimension 8 operators, the scalar, the longitudinal, and the transverse ones operators. So we had the previous observed limits, and we have improved a lot, okay? You see the difference here. It's much more constrained after this analysis results. Okay. Well, I will change to dark matter subject. Okay, good. I will change to dark matter results. I will not explain about dark matter. I took this summary, so I tried to put a summary of dark matter for more, so for the audience, for information, future information, and so we are interested in production for sure, production of colliders. We take here the mono something signal searchers, okay, and we have changed in the run 1 to run 2 to use simplified models instead of effective field theories, okay. Well, we know the mediator couplings change. It's depending on the spin, okay, spin dependent, the spin dependent, etc. And with so for dark matter, we started. So let me see. No, okay. So in the case of so, as I told you before, we focused on mono something searches, okay? we have mono Higgs, mono vector, mono gauge bosons or vector bosons, okay? And so we put some limits on the models from colliders. So here you see the profile, the distributions of the missing energy, since it's our the most important distribution. And here below, the exclusion limits for the mediators in the case of the pseudo-scalar mediator, we have less, so the mass is up to 400 GeV, so are excluded. You see here the observed line, yes, in red, okay, and so below 400 GeV is excluded, and also we put some upper limit on the invisible branch ratio for the Higgs, 125 Higgs. So the combined, we have here dot 53, okay, the observed here. So, okay, the combined for the combined channels, and here different for the different channels, okay, the combined. So we have an upper limit, and also constrained if we take into account the indirect detection from Fermi-Lat, the experiment Fermi-Lat. We have stronger constraints than ours for a pseudo-scalar less than 200, not yes, 200 GeV. Okay, here. Okay, so we try to. There are more results in the paper. Let's see. Yes, I show you also the. Oh, I guess it's not working. Maybe the battery. Can you hear me? It's okay? Okay, good. So here you see the translation for spin dependent and spin independent and the spin dependent cross sections, and you see here the CMS observed compared with different results, with different experiments for vector mediator and axial mediator, and so you can get very good information about dark matter limits from these plots. Okay. Any question for dark matter? No. Oh, good. No. Okay. So let's go to resonances. So the first one with an interesting but not, it's more or less hidden in the paper, yeah, because if you read the summary, it's not written in the summary, but so we have an analysis in the digits for the leptophobic Z prime and also dark matter, and so again using soft drop algorithm to deal with boosted events, to search for low mass vector resonances. Okay, so for the leptophobic Z prime, we had so you see here again the invariant mass of the soft drop jets. Okay, and here the anti-KT algorithm for fat jets, so we call it AK8. Okay, so this dealing with fat jets. Okay, and so we could include limits on for the dark matter. Okay, in the case of and an excess site, so small excess, is not evidence, okay? At 115 for the leptophobic Z prime. You see here, okay? So it should be investigated in the next run. It's an interesting, very interesting result. And combined DiGet for the dark matter searches. So with this leptophobic vector mediator, okay, was excluded from 50 to 300 mass, okay? So the mediator, so you see here the mediator, the dark matter mass from against the mediator mass. So from 50 to 300, it's excluded. This one is another collaboration, is another result I included here. This is another exclusion showed by CMS for lower Lumi. Okay, you have here 12.9 femtobar inverse. I put here the link, the paper for you to take a look. So this is another exclusion limit, an old exclusion limit in the same channel. Okay. So this is another. So this slight excess must be checked for in the next run. Okay. In the case of Di-Bosons, I will not give you details for sure. There are many. So the Di-Boson summary, I gave you here the link. But there are many signatures, okay? And you see here for book graviton, so the cross-section limits, okay? And for the W prime, based on all this analysis, okay? So for each one, you can see a different scenario, a different curve here to get information about the exclusion or the results obtained. Good. So the Di-Bosons, there are many. I gave you here the next slide for your information, a summary of this group in CMS that covers this new resonances to this standard model, to have standard model objects. Okay, so we have a vector-like quark production, resonance to heavy quarks, excited quarks, resonance to Di-Bosons, so the previous one. So we have here the limits for cross-section, and also so the observed, okay, in 95% confidence level. You see all information. So it's very easy to get information about the limits in 8 and also in 13 TV. So the vector-like quark single production. So many all analyses that are in progress or finished in this beyond 2 generation group in the CMS. Okay. If you want, if you want a specific detail of one of these channels, then I can try to get the physics analysis summary for you. Okay. Now, so we have new results for long-lived particles. So this one, the layered muons. We have so maybe you know what it means, and so the long-lived particles we have to decay. So they cross the detector, they stay in the detector, and they take longer to decay. in the case, in this case, decay into muons. And so we have all this, so it's only detected between in the gaps between the beams, okay? So it's not easy, so we have to stay taking data during the beams injection to try to get this information. It's not trivial, okay? So then after some work with triggers and also take cosmic ray, runs with cosmic rays, etc., we could exclude, if we assume lifetimes between 10 microseconds and 100 seconds, we could exclude the gluino, so models, so the long-life gluinos are in the context of split SUSY, and we have these multiple charged and massive particles, M-CHAMP, that appear in the modifier dry ion production, okay? It's very interesting. I didn't know this kind of particle. It's very nice to know new objects, okay? And we could exclude gluino mass and this massive particle in this range of mass, okay? You see here very nice plot showing the data and the observed data and the theoretical leading order prediction, okay? So very nice result. I don't know if it is related with that displaced you were talking about yesterday. The displaced jets is different? I don't know. Maybe something that could be investigated. Okay. We have also these particles stop in the calorimeter. Well, also gluinos were excluded, maintaining the same lifetimes as before. So the gluinos and the scalar tops, okay, the S-top, right? Yes, okay, here. And we have a mass exclusion for these models. So for gluinos here and for S-tops here. Okay. More information? No. Good. Well, SUSY. What we have from SUSY? Of course, SUSY, it's a huge group in CMS. Comparing Higgs and SUSY are a huge group analysis in physics analysis group in CMS. And you can see all results from SUSY. You have very nice plots, summary plots about the analysis and the exclusion limits. It's very nice in this link. Here, for the electrowake SUSY, you see different regions and exclusions, limits, and search regions for each search region. Yeah. So here you have different masses, and also it's I really don't understand very well this plot, but maybe André, you can you understand for sure. Well, anyway, here we have many. So the combined. So the point is in the electroweak SUSY we are searching for chargino neutralino pair production. Okay. Decay into W-boson, then the light supersymmetrical particle, yes, and the neutralino decay to the Z-bosons of Higgs. Okay, so this is the one of the one part of the analysis, okay? And here you see the exclusion limit for the W case, okay? And also for the Z case, okay? So you see here all the observed, you have so you see the theoretical, okay? And so the observed is this. In fact, here it's not even shown the observed, because no, okay. The observed is the full line, okay, for each color, each analysis, and here's the same. Okay, understood. Okay, so you see the differences and the exclusion limits for these several analyses concerning the electrolyte production in SUSY. And in the case of the top S quarks and also the direct dark matter, 4 models. So 4 models were adopted. So we have these 2 ones in this slide. We get more 2 in the next. So the final state, the 2 opposite charged leptons jets and the missing transverse momentum. For the T2 TT model, we have limit, so upper limit in the S top and the neutralino, so in these values for the T2 BW. So the difference is that here it decays directly, okay, and here it decays in B, and then another chargino, and then it decays in W and neutralino, okay? So this is the difference between 2 models. So there is another two types of diagrams here, okay? So here you see very nicely the limits, okay? Again, so the 2-dimensional plot showing you the limits for this for the mass of these particles. Here in the same analysis, but assuming now another chain of decay from before, yeah. So it's another chain, another chain layer of decay, and this is the so we have stringent limits combining all jets and single lepton channels with in different approaches. So we have a mass of this lepton, symmetric lepton here. So like this, okay, according this configuration. And so assuming different values of X, we get different exclusion limits values. So you see here the exclusion limits plots. And for the dark matter, assuming coupled to the top quark via a scalar or a pseudo-scalar mediator for the scalar, so no way to get particles, so with scalar with mass less than 100 GeV, and for a pseudo-scalar less than 50 GeV. Okay? Well, more constraints in SUSY. Also, for the R parity violating SUSY, we have gluinos excluded with 1,600 GeV. And so it's very close to the expected limit, because for the beams with higher masses, so the statistics is very low. So we could not differentiate a lot from the expected limit. Okay, so air parity with this exclusion again, and Well, neutrinos. We are reaching the end, okay? So be patient. So for neutrinos, this is a very nice plot, a very nice result, new one, very new. So it was accepted in the physics review letter. It's the strongest constraint on the mass of heavy fermions associated with the type 3 seesaw. So I show you here the lepton flavor democratic scenario where the mass is excluded below 840. In the tau-phobic case, assuming this scenario, we have masses below 900 GeV in the pure electron to 930 to the pure muon scenario, and also in the case of electron muon phobic case, mass less than 390 GeV are excluded at 95% confidence level. This is a new result for neutrinos, for the ones who are interested. So, okay, is the end. Well, the summary. So we are already 25 years. So let's wait for the next 20, 25 to see what happens. Yeah? We are going to upgrade the detector for the phase 1 and to upgrade to renew the detector for the phase 2 to support the high luminosity scenario demands. Concerning the results, we have confirmed the standard model, improving precisions. We had Higgs is taking, it's still finding results, is still taking new results, and but also focusing on precision program. Okay, we put stringent limits, dark matter, SUSY, exotics, as you see. So the type seesaw. You saw few excesses, so they are not evidence. So we need more data to take a look on it. And maybe if you are interested in heavy ions forward physics, not covering this talk, I can give you the way to get, or if you want some specific results, we have very nice results in this, in the forward physics, for instance, with the CT PPS. Okay, it's very good for the central exclusive production of WW, and also to put limits on the anomalous quartic gauge couplings. And so, big expectations for 2018. Concerning the Shannon, so I put here, so Shannon is 129, okay, so it's in between. And the PILAP, so this is this is the experiment needed. And so since the analyses are very similar to lead, okay, then we took data with this configuration, and also we improved MADGRAPH. We improved the Monte Carlo generators to be able to be available in time for the analysis. Okay, so it's not. It's fine. This is true. So this is the end. I don't. Everybody wake. Okay, no sleep. Sorry. Thank you. Sorry. It's indeed so it's a review of CMS. So it's very hard to inform all details of the analysis. So